We will now use the concept of electric field and the electric field intensity to solve problems. Alright, let's start with one. A charge of 40 microcoulomb is at the origin. What is the magnitude and direction of the electric field on the x-axis at x equal to 6 meter and b at x equal to negative 10 meter? Sketch the function E of x, electric field intensity as a function of x, versus x for both positive and negative values of x. Alright, first of all you need to visualize, got to draw a picture. And let me remind you, we did problems on calculations using Coulomb's law. And those who were not familiar with vector addition, finding the sum of two or more vectors by breaking them into their components. Now, I hope you have now some idea how to do that. We are going to use the same concept in this lesson again, because electric field is a vector quantity. If you want to find the resultant field intensity at a point, you should be able to add vectors due to several electric field vectors, and we will use the same method. Break each vector into components and then add them. Alright, this is a simple one. Let's do this one now. Since the field due to a positive charge is directed away from it, for positive x values the field will be positive, and for negative x values the field will be negative. Is that right? A charge of 40 microcoulomb is at the origin. So you have a charge of 40 microcoulomb placed at the origin. Here is the charge. Now the field to the right will be positive and the field to the left will be negative. I suppose that is not a difficult concept to understand, because the field lines due to a positive charge will all originate from it. The field lines will originate and go away. The field lines originate and go away. So on the right, the field lines are along the positive x-axis. On the left, they are along the negative x-axis. So if the field is positive on the right, the field is negative on the left. Now here is the charge at the origin, the 40 microcoulomb. We need to find the magnitude of the field at x equal to 6 meter. What is the equation we developed for the magnitude of the electric field intensity at a distance r from a charge q? You remember that one? E equal to kq over r squared. So you got E, this is the point at x equal to 6 meter. You got E equal to kq over r squared. K is 9 times 10 to the 9. Q is 40 microcoulomb, which means 40 times 10 to the negative 6. And R is 6 meter. So using that, we've got E equal to 10 to the power 4 Newton per coulomb. Now what is the direction of this field vector? This field vector will be directed away from the charge. Right, so this is 10 to the power 4 Newton per coulomb, directed in the positive x direction. The magnitude of the field at x equal to negative 10 will be again E equal to kq over r squared. The only difference there is now r is 10, r squared is 100, and that will be 3.6 times 10 to the 3 Newton per coulomb, and this is the point 10 centimeter to the left of the origin. And what will be the direction of the electric field there? The electric field at this point will be directed away from the origin. Now this field is in the negative x direction. Alright, now what is the next thing we need to find? Sketch the function Ex. What does Ex stands for? Electric field in the x direction. Remember, field is a vector quantity. It can be expressed as components, x component and y component. So Ex stands for the electric field in the x component. So you can see electric field in the x direction. The field will be very large as you come closer and closer to the charge. Field will be very large and positive, and as you go away the field reduces to zero. Is that right? I can actually draw that graph right here. So the field on the right will be like this. You see, as the point gets closer and closer, the intensity of the electric field will be very large. And as you start going away, the intensity becomes less, and it gets closer and closer to zero asymptotically. How about on the left? On the left, the field is negative, and at a point very close here, it will be a very large negative value. In other words, the field on the left will be like this. I'm going to draw with the blue line. Now that is the field on the left. You see that? So the field on the right, positive and decreasing, and the field on the right, negative and increasing. Well, what it means is it actually gets closer and closer to zero on either side. Okay. The function that describes the field density is Ex equal to kq over x squared. That is the expression, and if you can draw a graph of that, and look at that here, I used Maper5 to produce the graph of this function. And this represents how the x component of the field intensity changes with the values of x. Okay. The function only describes how the magnitude of E changes along the x-axis. Well, actually not. It also tells you the direction, because on the right side it is positive, on the left side it is negative. Alright? At a point very close to the charge, the field is either positive infinity or negative infinity, very large. And at very large distances, as you go far away, you can see the field get closer and closer to zero. Let's try another problem. When a test charge Q0 equal to 2 nanocoulomb is placed at the origin, it experiences a force of 8 times 10 to the negative 4 Newton. What do you think is what do you think is the reason for that force? When this charge Q0 is placed at the origin, it experiences a force. Well, it experiences a force because there is an electric field at the origin. Right? Otherwise, it will not experience a force. Now, part A, what is the electric field at the origin? In other words, what is the electric field at the origin which will exert this force on this charge? That is what we need to find. B, what would be the force on a charge of negative 4 nanocoulomb placed at the origin? If the force is due to a charge on the y-axis at y equal to 3 centimeter, what is the value of that charge? Well, I don't think you understood this question very well. But let me see if I can make it clearer as we go on. Well, here is the origin, and we have a charge Q0 equal to 2 nanocoulomb placed there, and we are told that it experiences this much of force. Well, that means there is an electric field there. It experiences a force of how much? 8 times 10 to the 4 Newton in the positive y direction. So this is the force experienced by this 2 nanocoulomb placed there. Now remember, this is a positive charge, is that right? Now tell me, if a positive charge is placed in an electric field, what will be the direction in which it experiences a force in relation to the direction of the electric field? Remember, the direction of the electric field is the direction in which a positive test charge would move. Well, that means if this 2 nanocoulomb experiences a force in the positive y direction, that means this is due to an electric field at the origin directed in the positive y direction. Alright? The magnitude of the field at the origin. Remember, the definition of electric field is force experienced by a unit test charge. A 2 nanocoulomb at the origin experiences this much force. Therefore, if you place a unit test charge at the origin, what will be the force? It will be the force divided by the charge. The force per unit charge is force divided by the charge. So E equal to F over Q0 will be the force per unit charge. The definition of the electric field is force per unit charge. So a charge 2 nanocoulomb experiences a force of 8 times 10 to the negative 4. Therefore, the electric field at the origin, which is responsible for that force, is force per unit charge. That is force divided by the charge. Convert the charge to coulomb. And that is 4 times 10 to the 5 Newton per coulomb J. So that electric field is in the positive y direction and its magnitude is 4 times 10 to the 5 Newton per coulomb. Now, if you place a negative 4 nanocoulomb at the origin, in place of, you remove this 2 nanocoulomb and place a negative 4 nanocoulomb at the origin, what will be the force that will experience? Well, F equal to E times Q, is that right? Force experienced by a charge is E is the force per unit charge multiplied by the charge. So force experienced by a charge will be E multiplied by Q. E is this, that is 4 times 10 to the 5 times negative 4 times 10 to the negative 9, and that is negative 1.6 times 10 to the negative 3 Newton J. So a negative charge. Now, if I have an electric field directed this way, a positive charge will move in the direction of the electric field. A negative charge will move opposite to the direction of the electric field. So, if a positive charge experiences an upward force, a negative charge will experience a downward force. I hope that is clear. So, if you now place a charge of 4 nanocoulomb here, it will experience the force 4 nanocoulomb. It will be the electric field multiplied by 4 nanocoulomb. That is 1.6 times 10 to the negative 3 Newton in the negative y direction. Right. So, we have now removed